So with the advent of the maser and the laser, increasing attention needed to be given to the diffraction loss of the mirrors and the spatial mode selections of the cavity. So Gary Boyd will explain us how the confocal resonator came about to help to solve these issues and the calculation he made with Jim on this confocal resonator.
I am here to give an overview of the history of the confocal resonator that Jim and I and others developed 55 years ago. A little background. I joined Bell Labs in July of '59 from Caltech, where I spent 9 years. It was a path followed by such as John Pierce, Dean Woolridge in 1936, and Charlie Towns in 1939. And you have to be at least 65 to know the importance of those early people, physicists of the 30s. Anyway, Towns's reputation at Caltech remained long after most graduate students and into my generation because of an acknowledgement in Professor Smyth's book on static and dynamic electricity to Charlie for checking all the answers to the problems in this most difficult required course on boundary value problems for all physics, electrical engineers, and mathematicians in graduate school. Charlie, we still remember that. Then Sputnik went up in 1957, which kicked everything into high gear, and I got lucky to be hired into research in Jim Gordon's department with Chapin Cutler, Rudy Kampfner, and John Pierce above us. Jim had joined Bell Labs in 1955 after his remarkable thesis at Columbia on the ammonia maser, which I remembered learning of in 1955 in graduate school seminar because it was noticeably important at the time. He rapidly became a department head pursuing solid-state maser research, as well as being the most eligible bachelor at Bell Labs, I quickly learned, until his wife Susie married him in 1960. When I arrived in July of '59, I was unaware of the Shallow and Towns proposal of December '58 in the Physical Review, extending the maser concept from microwaves to the visible and near infrared. Since by then, there were many talented researchers in masers, it is amazing that it was Towns and Shallow who pushed up the frequency by 4 orders of magnitude by pumping with an incoherent, recognizing that you could pump with an incoherent optical source or gas discharge. Arriving at Murray Hill from a microwave and plasma background, I surprised Jim in 2 ways. He forgot that I was coming, and therefore no desk for me, but also that I asked what I should work on. He suggested I read Shallow and Towns's, and I was intrigued with the description of the plane parallel Fabry-Perot resonator. People were talking ray optics at the time and estimating walk-off losses by tilting the mirror slightly. Also, it was suggested by Jim that I join a visiting professor from Oxford for just the remaining month or 2 who was trying for an optical maser in helium pumped by a gas discharge in a microwave cavity with a 10-centimeter internal Fabry-Perot separated by precision Invar rods. With a yellow sodium lamp, I had my first unpleasant experience at alignment of a plane parallel Fabry-Perot. Remember, we didn't have a laser or anything like that to align it with. Anyway, and I did observe the famous ring pattern of the Fabry-Perot. Now, various people at that time, including Shallow, were trying to choose materials for an optically pumped optical maser, and Javon, another classmate of Jim's from Columbia, was pursuing gas discharge pumping. At some point, Jim took us into Columbia University to meet Charlie and his graduate students who were trying optical pumping of metal vapors such as, I think, cesium. Then the world changed suddenly with Maimon's August 1960 publication in Nature of the ruby laser pumped with a flash lamp with the plane parallel Fabry-Perot resonator geometry. These were exciting times for sure. Next slide. I guess I can do it. Yes, thank you. Before that, though, we had actually started in '59 on the confocal resonator. Unfortunately, my notes were lost in the 2012 Sandy hurricane, so I'm not absolutely sure when, but I was distressed with the alignment of a plane parallel Fabry-Perot and went looking in reference books for a better interferometer and stumbled across what we now call the confocal resonator, first described by Pierre Cones as an interferometer in '56 and '58. As 2 spherical mirrors separated by their radius of curvature. The focal length of the spherical mirror is 1/2 the radius of curvature. So they share a common focal point. Hence, each mirror is imaged back on itself by the opposing mirror being at twice the focal length, which gathers all the light within the aperture, thus reducing diffraction losses, overcoming walk-off and things of that nature. I obtained a pair of spherical blanks and had them silvered for perhaps 1% transmission. Dielectric mirror suppliers were not readily available back then. As seen in Figure 2, the existing one, the great virtue of any curved mirror resonator is the well-defined axis is determined by a line through the two centers of curvature of each mirror. The ring pattern, when seen with a sodium lamp, is significantly larger, and the ease of alignment is just overwhelming. Now, in late '59 also, Fox and Lee at Homedale, about 30 miles away, were making an important advance in establishing the mode concept by numerically modeling Huygens' principle of diffraction to propagate uniform intensity. Well, they numerically propagated a uniform intensity from one mirror to the other and diffraction losses so that it settled down and formed a mode pattern on the opposite mirror of the Fabry-Perot. They repeated this many times until approximately a half cosine repetitious mode shape was established, with losses represented by the decrease in peak intensity with multiple bounces. They also could observe higher order modes. They gave a seminar at Murray Hill to a very packed audience of their diffraction loss results. At the question period, someone suggested that he should curve the mirrors, and I'm not sure if he said the separation should equal the radius or not. Gardner Fox answered that Gary had built such a structure, and the seminar ended. As we left, I asked our boss, Chapin Cutler, who that distinguished-looking older gentleman was, and I was only 27 at the time, and Cutler said he was Deming Lewis, and I should go talk to him. Back in my office at 5 p.m., I looked up his number and called him, and he answered the phone and walked down the hall, and was surprised to find him at the end of a rug row where all the secretaries had gone home. He was an executive director alongside John Pierce. We had a nice conversation over the next few days. He was previously an antenna expert and fully understood that a Fourier transform of a Gaussian was the same and probably a finite aperture could be handled. He said that David Slepian and Henry Pollack in the math department were working on an integral equation for totally different reasons, and I should speak with them. The long and short of this is that we set up a half self-consistent integral equation of self-reproducing eigenfunction between the reflectors. Lots of algebra is involved, and we were able to obtain closed-form solutions for finite diameter apertures with the confocal spacing, the solution of which are prolate spheroidal wave functions and their eigenvalues is a measurement of the diffraction loss. Next slide. In the large aperture limit, these eigenfunctions become Hermite polynomials times Gaussian wave functions. For a finite aperture radius A, the Fresnel number is A squared over B lambda and is plotted versus the diffraction. Oops, wait a minute. I got ahead of myself. Sorry. Yes, here we go. The large aperture, these functions become Hermite polynomials times the Gaussian wave functions. For a finite aperture radius A, the Fresnel number is A squared over B lambda and is plotted versus the diffraction loss per bounce is shown in Figure 3. The Fresnel numbers on the vertical axis and the diffraction loss get smaller to the left. Of course, a comparison with the plane parallel diffraction loss obtained by Fox and Lee for the Fabry-Perot is of great importance and is superimposed. Curved mirror, non-confocal resonators can easily have lower diffraction losses by several orders of magnitude. Once you see this figure, the immediate conclusion is forget the plane parallel reflectors. Curved reflectors or lenses or a continuously guiding medium between the principal reflectors is the way to minimize diffraction losses and form well-defined modes. After the confocal calculation of loss, Jim and I were immediately motivated in the Hermite a Gaussian mode approximation using Huygens principle to calculate the surfaces of constant phase both inside and outside the reflectors. The beam minimum radius is halfway between the symmetrical reflectors and spreads via diffraction. The waist diameter is related to this interesting length B we call the confocal parameter, representing the curvature and the spacing B by the formula given. A focused Gaussian beam expands by square root of 2 from the waist to the reflectors of radius B. All right, a historical update is in order. Fox and Lee and ourselves submitted our results to the BSTJ September 1960, following Maimon's August 1960 publication of the Ruby laser, which caused great excitement. The next significant advance was by Javon, Bennett, and Harriot's helium-neon gas discharge laser at 1.15 microns wavelength, published February 1961, using internal plane parallel mirrors. This was the first continuously operating laser, this gas laser, of Javon's and colleagues. Jim and I rushed to see this and suggested the use of curved mirrors, but that would take a year because Javon's laser had internal mirrors, which was mechanically very difficult. Anyway, immediately following Maimon's demonstration, everybody was scrambling for a ruby rod and a helical flash lamp. We learned to polish such a rod with a spherical curve while keeping the axis of the resonator within the small diameter of the rod. A poor quality ruby crystal lased easily, and I reported such at the Berkeley Quantum Electronics Conference, March 61, following Javon's publication. At that point, Herwig Kogelnick had joined the labs in January 61, to Jim's great excitement, as they shortly dominated both singles and doubles in the tennis ladder and Herwig on the chess ladder. As a boss or colleague, Jim was non-threatening and a catalyst and a stimulant while puffing his pipe. But in racket sports, being non-competitive does not apply to Jim, being, as we mentioned, the national champion in platform tennis, invented in his hometown of Scarsdale among the country club set. Okay, next one. Kogelnick and I started working together to generalize the confocal resonator theory in various ways. Kogelnick also joined in the effort to improve the gas laser with the Brewster windows and external mirrors. Kogelnick and Rigrod's results display visually Hermite Gaussian modes in great detail. They also measured the higher order mode splitting of the transverse modes of the non-confocal resonator. In the confocal resonator, higher order modes are often degenerate. With Kogelnick, our original non-confocal resonator was extended to two different radii spherical surfaces, say B1 and B2. It was found that the spacing D, that if the spacing D exceeds the sum of the two curvatures, B1 and B2, the structure is high loss, and that if D was between the values of B1 and B2, it was also high loss. This is the resonator stability diagram. If B1 equals B2 equals D, the confocal spacing, which is right there, this is on the critical point of instability or a high loss region. And as long as I'm pointing, I will point out this is the plane parallel extreme, and this is the approaching the concentric sphere regime. So you can operate in any of those regions. But one should not work at precisely the confocal spacing. A two-dimensional stability diagram from Fox and Lee and ourselves shows the full range of operation. The reflectors must not be separated by more than the sum of the radii of curvatures. The plane parallel resonator did not become significant again, that's the plane parallel one, until the VCSEL era came along many years later. But our theory in the near field of the beam waist also applies there and gives the mode splitting. Going right back to our first paper with Jim, I could find a formula for the mode splitting separation of the higher order modes, which when measured allowed us to easily calculate the Gaussian beam radius W0 of the VCSEL. So after 40 years, I was still working on modes. And a resonance structure can easily be extended to a periodic sequence of lenses, such as used in submarine periscopes, which images every other aperture on the next, so that there is no light lost in a long tube. We and others have pursued this extensively. Jim and Hervig published on the equivalence relations, and Jim on the circle diagram, and Kogelnick and Lee on other famous papers. So I hope it is fair to say that the confocal resonator launched us into Gaussian beams as a normal mode in many optical resonant or periodic systems, with modes defined by Hermite or Laguerre polynomials. After a delightful collaboration with Jim and Hervig, Ashkin and I went off to investigate nonlinear optics with Gaussian beams in anisotropic media such as lithium niobate, where the pointing and the propagation vector make a small angle, say 5 degrees, with one another. From this, you can calculate parametric oscillator thresholds, which can be determined, and it gets very complicated, and I discussed this with Jim on various times, but it is understood in anisotropic media. In conclusion, one of the luckiest things in my life was to have the pleasure of working with one of the absolutely smartest and nicest people I have ever known, and that is Jim Gordon, during this exciting time. It was also always rewarding and a pleasure to enter his office for interesting discussions. As an example, I come from a long line of only children, and he suggests only children, and when I volunteered this, that we'd had our one child, he suggested that we have a spare. And, and we are now tended to in our declining years by our spare, our geriatrician daughter, which seems quite appropriate. Anyway, Jim made many important contributions in many fields. I was privileged and lucky to work in one of them. His was a life well spent, as others will attest to. Thank you very much.